Let's look at the moving clock. Let's suppose at one point in time it's sitting like that. It's moving to the right at speed u, and over here is frame S, and we are looking at this clock moving in frame S. There is a flash of light at a certain time, and a little time later the clock has moved to this position. The flash of light, when looked at in the rest frame, will have got to the mirror, and so it will have got to the mirror, but seen in frame S, it will have taken this path. Then the light signal returns back to the detector down at the bottom, so a certain time later the clock has got to this position and the signal returns to the detector. Let's now look at some distances. We notice that this is a Pythagoras triangle, and the time it takes for the signal to get from the lamp to the mirror and then back to the detector is a time delta t. So the time it takes to get from the signal to the mirror is half delta t. Since the clock is moving to the right at speed u, this distance here is u times half delta t. The light signal travels a distance c times half delta t. And this distance here is d, and we have already established that d is equal to c delta t naught over 2. Let's now do some maths to solve for delta t in terms of delta t naught. So let's take one of the right angle triangles from our previous diagram, and we know that the square of the hypotenuse is equal to the sum of the square of the other two sides, Pythagoras' theorem, and we know that that's the distance traveled by the light signal. This is the distance traveled by the light signal when the clock is at rest, and this is the distance traveled by the clock. So the square of the hypotenuse, c squared delta t over 2 all squared, is equal to c squared delta t naught over 2 all squared plus u squared delta t by 2 squared. This factor of 2 below the line, when squared, becomes a common factor 1 over 4 for all three terms. So we can multiply through by 4, and we end up with c squared delta t squared equals c squared delta t naught squared plus u squared delta t squared. Now we want to solve for delta t, so we take this term and we subtract it from both sides, and we take out the common factor of delta t squared, so c squared minus u squared delta t squared is equal to c squared delta t naught squared. We now divide through by this c squared minus u squared to obtain delta t squared equals c squared divided by c squared minus u squared, all multiplied by delta t naught squared. So now we have delta t squared on the left hand side and delta t naught squared on the right hand side. Continuing with that, we have delta t squared equals c squared divided by c squared minus u squared times delta t naught squared, and we're going to divide this factor by c squared top and bottom, so we get 1 divided by 1 minus u squared divided by c squared. That factor multiplies delta t naught squared. And so we are able to finally, by taking this positive square root of both sides, find that delta t is equal to 1 divided by the square root of 1 minus u squared over c squared times delta t naught. So we have this formula: delta t is equal to 1 divided by the square root of 1 minus u squared upon c squared times delta t naught. And this, as we'll see in a moment, is time dilation, which means that the delta t is bigger than the delta t naught. So the time taken for one tick of the clock when it's moving is longer than the time taken for one tick of the clock when it's at rest. So time slows down for a moving clock. The factor 1 divided by the square root of 1 minus u squared upon c squared is very important in special relativity, and that is called the Lorentz factor. It's given the symbol gamma, and it's a function of u, and another way of writing it is 1 minus u squared upon c squared to the power minus a half. Now, gamma is always greater than or equal to 1. We see that if u is equal to 0, then gamma of u is equal to 1. And when u tends to c, so u tends to c, then gamma will tend to infinity. Here is a plot of the Lorentz factor as a function of u divided by c. So we see that when u divided by c is 0, the Lorentz factor is 1, and then it stays close to 1 for a large part of the domain until about 0.6, where it starts to increase and then increases very rapidly, tending to infinity as u tends to c, so as u upon c tends to 1. To conclude, we can write the time dilation formula very simply as delta t is equal to gamma delta t naught. That expresses time dilation. Just to note that delta t naught is called the proper time interval, which is the time interval in some frame between two events that take place at a point that's at rest in that frame.